Okay, welcome back everyone. So our next speaker is Manas Kulkarni, quantum trajectories and page curving entanglement. Please, Manas.
Thank you. Let me start by thanking the organizers for giving me an opportunity to present these results in this wonderful program. So today I'm going to speak about page curve entanglement and quantum trajectories. So I'll be speaking about two parts. One is on page curve like dynamics in a freely expanding fermionic gas. The work is available here, and this is the work done with Madhumita, who is a postdoc at ICTS, and Abhishek, who is my colleague at ICTS. And in part B, I'm going to speak about this kind of page curve entanglement, quantum trajectories and effective interactions. And this is the work done with Katha from IISER Pune, Preeti, who was a visiting student here and now in Luxembourg, Atharva, who's a student at ICTS, and Bijay, faculty at IISER Pune. Let me just start with the general platform. So I'm going to consider a quantum system that is basically coupled to an environment. Okay, so this is my sort of, this is the setup, and one can ask certain questions like what are the number of particles that leave the system as a function of time, and this is the same as number of particles that enter the vacuum. So imagine a quantum system that is just coupled to a bath, and then you just connect it and you sort of have a filled quantum system, and you ask these questions: what is the number of particles that leave the system, and so on. What about density profiles, currents and number fluctuations? How long does it take to empty the system? So it's a large vacuum. So the system is attached to a large vacuum. What about the entanglement entropy between the system and its complement? So the complement here is the environment. So what is the entanglement entropy between system and its complement? Is there some collective description that captures essential features of such a setup? And is there a connection between entanglement entropy and, let's say, thermal entropy within the system? And what happens to imperfections or effective interactions, weak measurements? How do they get encoded in quantities mentioned above? So my setup is basically a system which is coupled to a much larger system. Okay, so this kind of thing has some relevance to black holes. So if you want to understand entanglement entropy, so this is going to be my plot. So if you have entanglement between black hole and the radiation, starting from an unentangled initial state. So if you have an unentangled initial state of your system, initial entanglement entropy is 0. And then let's say particles get radiated into the vacuum, and these particles that go into the vacuum get entangled with those in the system. So entanglement entropy initially grows, and then after some time, a lot of particles go into the vacuum, leaving very little in the system. So the entanglement between those in the vacuum and the system again has to decrease. And so it basically, you expect it to decrease. And this maximum is what I call page time. And this location of the maxima I call page time, and this I call page value. Okay, so I hope the setup is clear. So you have lot of particles and nothing in the vacuum. So initial entanglement is 0. Then particles go, then the entanglement builds. But after some time, most of the particles enter the vacuum. So again, the entanglement between the vacuum and the system is 0. So you have this page curve. So this is basically interesting from the point of view of black holes, where they say that as the black hole radiates, the effective Hilbert space dimension of the radiation increases, and there'll be a corresponding increasing entanglement entropy. And this increase has to stop when the black hole and radiation have the same Hilbert space dimension, and beyond which the entropy has to decrease after the black hole eventually evaporates. So for the rest of my talk, you don't need to know anything about this. So I'll just go back to our setup. Okay, so you can completely forget this connection at the moment, but it's an interesting connection in black hole physics. Okay, so now let me get back to the system. So this is my system. It's a filled Fermi system. I fill it completely with fermions, and I have an empty reservoir. And then I let it evolve. And so this GC is the hopping between the system and the bath, and G is hopping within the system and within the reservoir. Okay, so this is a very simple setup. And the fact that GC is not equal to G is why we call it a defect, and it is sort of important. I'll come back to it later. Okay, is the setup very clear? Is that you couple a small system to a semi-infinite tight binding model. Okay, please ask me questions if there are any. Okay, so now the initial state is a completely filled system. So since this is a quadratic Hamiltonian, you can do very extensive exact numerics because you just have the total Hamiltonian. You can calculate the correlation matrix which is given by this dynamics. And once you have the correlation matrix, you can extract things like density, current, the one-Neumann entanglement entropy, particle fluctuations, and so on. So because you have this access to this correlation, Ci dagger Cj. So here Cij is the correlation matrix of the entire system and the bath, but you just take part of the, you take the system part and extract all these quantities. You can also extract quantities in the reservoir sector. Okay, so this is as far as exact numerics is concerned. Now, in this particular case, you can actually ask, so how do we do the numerics? So numerics, you can consider system to be of size 600 and bath to be of size 6000. So practically the bath is very, very large, and you basically do the numerics. But you can ask, is there some collective theory that can describe this system? Okay, so it turns out that in this free fermionic system, you can describe the evolution on some large length and time scales by generalized hydrodynamics. And the idea is that the system is a gas of quasi-particles that carry fixed momentum levels and have this phase-space density. So basically, I can discuss the details with those interested, but basically you can write a semi-classical description of this form, where this is the coarse-grained Wigner function, or you can call it the phase-space density. Basically, you need to, this n of x, k, t, so this n is a function of x, k, and t, and from there you can try to extract quantities. So here we are sort of forgetting microscopics and trying to get some sort of collective behavior. So this equation, we need to solve it with appropriate boundary conditions. And from this, we can extract density, average current, and something called hydrodynamic entropy. Okay, so this slide is different from my previous slide where you just do exact numerics. And then if you manage to solve this, you can essentially get some analytical solutions. Okay, so recall that this is a simple equation. And if you have an infinite line, then this is very easy to solve. You just boost the function. So this is a solution. But in our setup, remember that the system is finite and the bath is infinite. So you have to take into account all sorts of things like particles from the system. So particles from the, so this is a system is finite and the bath is infinite. So the particles entering here and then reflecting back, reflecting again, and then going. Many such processes, maybe one reflection, two reflections, because this is a finite system. This is a finite system. Okay, and this is infinite bath. Infinite bath. So if you consider all those reflections and transmission processes, you can actually write this n of xkt. Okay, so and the GC, the defect GC is encoded in this reflection and transmission coefficients. Okay, so now let's say that you somehow have n of xkt from some collective semi-classical description. You can then extract the density profile. The density profile is nothing but you just integrate over k and you get rho of x comma t. So there's a t, there should be a t here. Okay, so you can get the density profile. You can also calculate something called Yang-Yang entropy or thermodynamic entropy or hydrodynamic entropy. So you don't have access to one-Neumann entanglement entropy, of course, but you can calculate some hydrodynamic entropy. Basically, it is n log n plus 1 minus n log 1 minus n. If you integrate it in the system domain, we call it system hydrodynamic entropy. If you integrate it in the reservoir domain, we call it reservoir hydrodynamic entropy. Okay, so this is the idea, and this is how the phase-space dynamics evolves. So you have this initial condition. So it's a fully filled fermionic system. So in phase space, it is just like a box, and then this is how it evolves in phase space. Because you have to evolve it in in phase space. So this is how it evolves. Okay, so now this is all free fermionic system, and so I'll just go to the results. So let us focus only on the column, the first column. So this is the density. This is the density, initial density. So initial density is a domain wall because the system is filled, and then the domain wall slowly evolves. But you see here, because the system is finite, you have all sorts of things here, but this is how the system evolves. And then the particles are radiated into the reservoir. Here from about 30 to infinity is the reservoir. So you have density that is just going away into the reservoir. Any questions? Okay. So this is how density evolves. And here, basically, if you do this exact numerics that I mentioned and the hydrodynamics, you basically get perfect agreement between numerics, between brute force, direct numerics, and hydrodynamics. So this is the entanglement entropy. So let us focus only on the blue circle. This is the exact entanglement entropy from numerics. You see that the entropy increases, goes through this page value, and then decreases. Yeah. So conformal defect is when the reflection and transmission do not have momentum dependence. So that's the thing. Actually, so there are some minor details between different defects, but we can discuss that later. Yeah. So by and large, the plot is like this. And the interesting thing is, if you calculate the hydrodynamic entropy, it really traces the entire page curve. But if you calculate the reservoir entropy, it just goes and basically is basically monotonically keeps increasing. Okay, so there is a collective theory which recaptures the page curve here and agrees with the numerics. So another interesting quantity is this particle number fluctuations, which also gives a page curve like behavior, which is also very physically obvious that it should go up and go down, but nonetheless one can extract some exponents from hydrodynamics and so on. So this is the conclusion of part A. So basically, in the free fermionic system, we got this page curve, the blue ones exact, and the green ones are from hydrodynamic entropy of the system, and orange is from the hydrodynamic entropy of the reservoir. And this is very similar to the entanglement entropy of a black hole, where you get this page curve. But if you calculate the entanglement entropy of the radiation field, according to Hawkins' semi-classical calculations, it actually keeps increasing. So there is some sort of similarity, and so we are able to basically have a friendly platform to capture essential features of a page curve. And semi-classical enables us to understand analytically the page curve, both at late and early times. And this thermodynamic entropy of the system agrees remarkably well with von Neumann entanglement entropy. But reservoir entropy only agrees at early times and keeps on increasing. And this is like radiation entropy from semi-classical theories keeps increasing. Okay, so now let me go to the next part, which is closer to quantum trajectories. But please ask me if there are any questions. Yeah. Yes. Yeah. So we verify that in free fermionic theories, we see that the particle number fluctuation and the entanglement entropy basically are proportional to each other. But we see that around the page value, there is a discrepancy. So, but the early time is very good agreement. Yeah. Okay. So now, what is the impact of effective interactions or imperfections encoded? How is it encoded in usual quantities of interest? Are there some universal properties? So let me now consider this system. So again, you have this system, and then you have this reservoir. So we'll just discuss two cases. So one is the case when we call it the probe clean case, where the system has these additional probes. So this is like this dephasing Lindblad terms, and the vacuum is your tight binding model. So it's a free vacuum. And you can also ask, what if the whole thing also has probes? So even if the vacuum has probes, right? So if the whole thing has this dephasing Lindblad term. Okay, so now question is, how do you address these questions that I asked before in such systems? So it's important to keep in mind that these probes, basically you can think of them as mimicking interactions by inducing scattering effects. By this we mean that if you have a free system, typically transport is ballistic, spread of wave packets is ballistic, but if you do the same thing with dephasing probes, you will get conventional diffusive behavior. So in some sense, it mimics generic quantum chaotic non-integrable systems. But even more commonly, basically it mimics environmental imperfections. You actually have these dephasing terms. You can ask what happens if the system is embedded in a phonon substrate or something. You may actually have this imperfection, and how do you deal with this to calculate such quantities? And they make a big difference. Okay, so this is the dephasing term here. And LS is the size of the system, LR is the size of the bath, and L is the total size. Okay. So here again we do numerics where LR is much, much greater than LS, at least an order of magnitude greater than LS. Okay, so then, so Lindblad equation is sort of, well suited to study dynamics and steady state of expectation values that depend linearly on the density matrix. But things which are inherently nonlinear need a careful unraveling procedure of the underlying density matrix and so on. Right? So if you want to calculate entanglement entropy, what do you do? One-dimensional entanglement entropy and things like that. So now here, for such as Lindblad equation, we sort of study two kinds of unravelings. So first unraveling is stochastic unitary unraveling. So here we have on-site fluctuating noise, which is added to the Hamiltonian, thereby making the evolution stochastic while maintaining its unitarity. So this is, I'll come to this, we call it stochastic unitary unraveling. So you basically add noise to the Hamiltonian, and effectively it mimics a dephasing Lindblad equation upon averaging. The second one, of course we heard talks in this program on quantum state diffusion, where when unraveling mimics weak measurements of local particle number at each site. So we study these two kinds of unraveling. Now under this unraveling, you can ask this question, what happens to this thing? Okay, just to sort of, before I go there, in the free theory, the growth of entropy is typically linear, okay, when you have a defect. So there's a linear growth in entropy, and the page time scales linearly with the system size, and the page value also scales linearly with system size. So let's just remember this. So this is what happens in a free theory. This is a free theory. So now we can ask what happens to these kind of things. How does it scale in this kind of things? And what are the number of fermions radiated into the reservoir? Is there a relationship between entanglement production rate and current, and so on? Yeah. Yeah, so I'll come to that. So that is why we do this unraveling. Yeah. So note that we have two geometries, but okay, that's not very important when only the system has probes, and which we call PC, and we have geometry where system and reservoir have probes. But I'll come to that. So basically that is the problem, right? So you can calculate rho log rho, but it won't be one-dimensional entanglement entropy. And then if you really want to use the density matrices, then you'll have to do something like negativity and so on. So which has its own set of issues. So, but let's go to this unraveling. Okay. So before proceeding further, let me just briefly recap unraveling procedure. This is a time lost or time remaining? Remaining. Okay. It's going there. Okay. So okay. So then let me discuss this unraveling procedure. Okay. So stochastic unitary unraveling. So let's recall that the Lindblad equation is this. This H is our non-interacting Hamiltonian. So this describes the time evolution of the mixed state, as you were saying, and which is ensemble average of pure states. So these pure states evolve stochastically in time. So under this SUU protocol, the lattice system is subject to on-site fluctuating Gaussian noise at each lattice site I, and it mimics on-site imperfections. So most of the audience know all these things, but anyway, let me just, in this context, I will try to just recap this. So this is the stochastic Hamiltonian, and you can write this quantum trajectories. These are so basically here. So you have this wave functions here, and from this, I want to extract my quantities of interest. Okay, from this quantity, I want to extract my quantities of interest, and some important things. LP is the location until which the probes are placed. Okay, so all this is fine. So now once I have this, yeah. So important point is this one. This is stochastic unitary unraveling. Okay, so this is where it appears. So once you do this, you can write the quantum trajectory in this way, where U is a L cross LS matrix. L is the total size of the system, and LS is the total size of the system plus reservoir, and this is size of the system. So U is a rectangular matrix, and once you have this U, you can actually extract the correlation matrix for a given trajectory. Okay, so this is Xi, this is for a given trajectory. You can extract this correlation matrix. So once you extract the correlation matrix, you are in business. You can calculate whatever you want for a given trajectory. Okay, so and from this matrix we can compute various quantities, including entanglement entropy. And at the very end, we can perform average over the trajectories. Okay, so this is and these are the two cases. So this is mimicking imperfections through Gaussian noise. Okay, so now I will go to the next unraveling, which is quantum state diffusion, and then I will present the results with these both unravelings. So in QSD, it mimics the same Lindblad dynamics upon averaging, but the stochastic dynamics under QSD protocol, it describes evolution of a quantum system subject to continuous weak measurements of local particle number Ni. So, okay, so these measurements are performed by coupling the system to a detector and making projective measurements of the detector. Okay, so basically the analog, the QSD, the SUU analog will be this equation. So you can write this will be the evolution of the wave function, and you can again reduce it to a form like this, where it is very different from the SUU protocol because of this non-linearity here. Okay, and then you can again recast it in terms of these U matrices, and then again extract the correlation matrix. So presence of Ni makes the dynamics non-linear. So there's a measurement back action, and so this is how it is different from the SUU. But all this upon averaging will give me the same Lindblad equation. So if I'm interested in occupation number, current, everything should give me the same answer. But if I'm interested in entanglement entropy, then it will depend on the kind of unraveling. Okay, so now let me so now let us focus on maybe one setup here. This is a probe clean. So this is one of the motivation for this is you can ask that, okay, my system is, okay, it may be effectively interacting or it may have imperfections, but my vacuum is clean. So that is why there is this motivation. This kind of motivation is, you don't really think of vacuum as something else. You think of a large system and you just not bipartition it. You take a small part and say 95% of it you call the rest of the system. So that will be this kind of situation. Okay, so I hope the motivation is clear. Okay, so now what do we see? So now let us go back to this plot here. This is free theory. So now let us look at this entanglement entropy as a function of time. So now we see that there is a huge window where it grows as square root of t. The entanglement entropy grows as square root of t. So this thing here is now square root of t. The page value, basically the page value here again grows like volume law, Ls, and you can actually get very clear estimates of how it falls, decays in time, and so on. Okay, so this is what happens with entanglement entropy. So and in this case, I probably didn't show here. You can ask the number of particles that enter the reservoir, how does that scale with time? And it turns out that the number of particles that entering the reservoir scales as root T. Okay, the way, so both the number of particles entering the reservoir scales as root T, and the entanglement growth is also root T here. So this is the stochastic unitary unraveling. Note that these two things are not measurement based. Okay, so these two things are not measurement based. So let me first do the SUU first. So then here, here this is the probe case. More or less you see the same physics. You get root T here, but we see very different decay exponent here, which we still have to understand. But basically we see that we get root T, and the page value goes as volume law. So I just want to mention that most of the literature do bipartitioning, and they calculate the entanglement entropy, and they ask how the steady state entanglement scales with system size. So here ours is not a bipartition, because if we do a bipartition, we'll never realize the page curve. We want the system to be much smaller than the bath, so that we can get the page curve. And so we have to analyze the page value as a function of system size. Okay, so this is without measurement based protocol. Now this is measurement based protocol. So let us again go to this probe clean setup. So here we see very different. So we basically see log T growth. So in measurement based, so this thing in measurement based will scale as log T. Will scale as log T, and it will decay in some way. And here the page value basically goes through subvolume to area law. So we actually see that this is the plot. So basically the page value first seems to go as subvolume log LS, and then it becomes a constant. And there is also a region where you get volume to subvolume. But to capture volume to subvolume to area in one plot is difficult, basically. Okay, so basically we see subvolume to area law growth, and here basically we seem to have some strange behavior of log T, very slow growth of entanglement. It happens in certain setups, but we still have to understand this, and here we see subvolume. I mean, the guess is that here eventually it will become area, but it's very complicated numerically to capture that. But the idea is that the QSD is very different from the SUU, which is sort of obvious because measurement weakens entanglement. But now we have a proper notion of entanglement entropy in these trajectories. Okay, so any questions about this? Yeah. Yeah. Under which protocol? QSD. Yeah, no, of course it depends on gamma. If gamma is too high, then the entanglement growth will be extremely small. So basically this whole thing will just become flat right away like this. Yeah, that happens, yes. So, and if gamma is too low, then it will look like you will get volume law, but eventually for large enough LS, it will become subvolume. Yeah. But notice, okay, anyway, so that's the thing. Okay, so gamma here is basically mimicking measurement rates. Okay, so and gamma here is basically, in this case, gamma is mimicking strength of imperfection. Okay, so now there is sort of a conjecture, or you can find that there are these kind of predictions that the entropy production rate and current are related. Okay, so the point is that so here by current I mean the current from the system to the bath. Okay, and we actually verify that under the SUU protocol, the non-measurement thing, that this actually holds. Entropy growth is basically proportional to current. Of course, it will not hold in QSD, because whether it is QSD or SUU, this thing is same, because this is just current. So this is just same, but clearly entanglement is very different between the two protocols. So we see that in the SUU protocol, this seems to hold quite well actually. And this statement is basically, if you rewrite this statement, So it's where ds by dt is basically proportional to current, but current is basically something like dnr by dt, right? Where nr is number of particles that are entering the reservoir or number of particles that are leaving the system. So basically this translates into S being proportional to nr, okay? So basically it says that the way the number of particles exit, the entropy also scales in that way. But that is not obvious, because just because the number of, it doesn't mean that just by, I mean, how much entanglement they carry is different information, but it works in this SUU protocol. Okay. Okay, so so this is my conclusion. So we examined entanglement entropy, page curve in an effectively interacting system following quantum trajectory approach, and depending on the unraveling procedure and the setup, we observe distinct time dynamics for growth and decay of entanglement. And SUU protocol always leads to diffusive growth. Okay, so square root of T behavior, and QSD protocol due to local monitoring is much slower, and we find strong numerical evidence supporting relation between entanglement production rate and particle current up to the page time. So that is the thing, and we have a lot of open questions here, but one of the things we are trying is to calculate these things in an actual quantum interacting system, such as spin chains and so on and so forth, and trying to find in this probe setup some more analytical calculations and see if we can explain these exponents and so on. Thank you.
Thank you very much. Are there any further questions? Yes.
I had two questions. One was like, if you look at individual trajectories and look at the entanglement growth, and how much are the fluctuations between trajectories? Is it kind of small or it's very typical?
Yeah, so okay, so the thing is, I think so Kata will verify this, but the fluctuations are not very high. So each trajectory actually satisfies the same curve. So this is yeah, this is something that is important to, I mean, in fact, Abhishek also pointed out this, that that whatever we see should hold for individual trajectories. So this additional averaging is not really needed. So it's some kind of averaging, but for each individual trajectory, you expect to see the page curve. And in fact, if I take the individual trajectory and do some moving time average, I should basically get I should basically be able to smoothen out without even doing averaging over trajectories. So yeah.
Other question I had was like, I mean, with the dispersive probes, I think the hydrodynamics is diffusive hydrodynamics, right?
Yes, yes.
So I mean, should that, did you check if that reproduces the?
So this is something we are still trying. So the question is, the phase space dynamics should be, now we should make it diffusive dynamics and do the same. It should reproduce, but that's what we are trying. So, and our hope is if we try that, then we can explain these strange exponents, some of these exponents that that are not very clear where they are coming from hydrodynamics. But in fact, hydrodynamics might be able to do even better here because it's effectively non-integrable and it may be as good as the previous.
Hi, thank you for the talk. So I have two questions. First is like, if you compare this with the page curve of black hole dynamics, like which does it like how well does it match? And the second question is, normally in like black hole literature, people compare like black hole dynamics with this SYK model, something which has all-to-all interaction and random couplings. So do you think that that would be better model for that? I mean, I don't know how easy it is to simulate that, but would it be better?
Okay, so let me answer the second question first. So the point is that there are works on SYK. In fact, I would suggest this review on SYK and its generalization, entanglement in SYK and its generalizations. There are papers that are proposing this. I mean, there are papers on entanglement dynamics, and in fact, I think even on some possibility of some page curve. Like you have two SYKs, you need 2 SYKs, right? So, and then if you calculate the entanglement dynamics between the 2 SYKs, you should basically get this. You should basically get this. But the problem is, in our case, our system is much smaller than the reservoir. But in SYK, I'm not fully sure how will that look, because here what is the analog of the second SYK being much smaller than the first? I'm not so sure. But I think in principle, you should be able to get this in these SYK models. Regarding your first question, regarding your first question, okay, so that, that is not clear at all. So basically, these are very, very friendly toy models that we have that mimics the entire page curve. But what comes out of a true black hole physics calculation and whether one can compare it, in that sense, probably one has to look at SYK models. So, but what is good is that here you can do a lot of analytics and very, very extensive numerics and characterize these things.
Yeah. Do you get a phase transition in the volume you're? Because many people talking about phase transition, but they do it on the closed systems.
Yeah. Not very confident of answering that, because so the point is that it's hard to say whether we'll get. At the moment we get volume to subvolume crossover and subvolume to area crossover. So it's not fully clear. Yeah.
Okay, thank you very much. Let's thank the speaker again.
Thanks.